Hello and welcome to another Solana tutorial. Today I want to have a look at the Solana program Entrypoint. You know, the thing that is starting a Solana program. How all the data gets into your program. I want to have a look at that. How that's actually being deserialized. Well, really I want to look at how it's serialized. I want to look at in what form do those bytes come in such that we can deserialize them. And then I want to have a look at different Solana entry points. I mean, it's always going to be the same in the program, but how you treat it, how you deserialize the data, this can be optimized. So there are already different implementations of entry points. And that's what I want to have a look at, like how you deal with, the data coming in. And this is all part of the series of compute unit optimization. That's ultimately what it comes down to. We want to optimize, but therefore we first need to understand what is even happening such that we can optimize. And really, this is just going to be a little bit of a deep dive. I'm not sure how deep I'll actually get today, but we're going to focus on the entry point and just have a look at that because I'm curious. Last time, in my last video about C programming, we found that input array that had all the data and I had a wrong assumption of what that data is. And that's when I got curious. So what is that? And today I really want to look into that, what that really is. So let's get started right away because I'm already so excited. Here, that is the C program that we had a look at last time. This program, we had a look at the transfer lamperts program that basically just, moves some lamperts around. But we were using this sol account info, and this is all C, by the way. We were developing in C. We will have a look at Rust entry points as well. But the really interesting thing is this, the entry point function that takes this input pointer to unsigned 8-bit integers. So essentially bytes that we then interpret in a certain way. I basically want to do a deep dive on this, because that's where this input becomes those parameters. So if we want to find out what that input really is, we can look at one of the examples like this one and read the source code, or we go through documentation, or both. And really, we're going to do both. And we're going to cross-check if they say the same things. And since reading C code might not be super easy for all of you, I think I'm going to start with docs, because they literally exist such that you don't need to read source code. In the beginning, when people started developing programs on Solana, they all had to read source code because there was no docs. Good old times or bad old times. There's Deserialization now, so we try to make that better. Anyway, maybe one simple thing here checks that those two things are present, and then it already does the first thing. It sets the KA number, which I think is the number of accounts read. It sets that number to the first byte of the input. Oh no, hold on. The first 8 bytes of the input, because that's a U64. So first, it takes the pointer to the input, casts it to a U64. C is so much fun. And then makes a pointer of that. So yeah, it's just casting it to a UN64 pointer. And boom, we have the first 8 bytes in this value. And then the input plus equals. C is so much fun. You can just plus equals a pointer. And then it steps over this size in uint8s though. So that's the amount of uint8s that it steps forward, because that's the type. And the size of a uint64 should be 8. So the input plus 8 basically just moves the pointer along, such that the input pointer now points to the next 8 bytes. So that's fun, but we're looking at C code, and it would be much easier if we just had, text. So let's go find out what this entry point really takes. Program entry point. So in Rust, with this entry point macro, we can define a function with this signature where we get the program ID, the account infos, and the instruction data. But that's already deserialized, right? It's already the deserialized account infos and the remaining instruction data. So when you call a program, those are the two things that the program receives. What are the accounts and what's the instruction data? But let's go one step before. I want to find out how it gets there, like before it gets there. Where's this entry point? How is it implemented? Where is it defined? I think I saw something in the CU guide about that. Ah, Wait, there. I mean, that took a while to find. Different entry points. We got the Caveman Loverboy entry point. We'll look at that later. We've already seen this one at the nano token. We haven't really looked at it, but I think it's in there. Solana.com/docs. A single entry point on Solana handles all instructions. Yeah, that's how Solana does it. That's also not really what I want. I will find this in the doc, and otherwise I will just read source code. Yeah, that's helpful information. Ha! What is that? Input parameter serialization in the loaders. That's where the info is. Programs are deployed with and executed with runtime loaders. Currently there are two. The BPF loader and the old one. We have a BPF shared object. That's the SO file. Write it into account, make it executable. That's how it is being deployed. When an instruction is directed at an executable SPF program, the loader configures the program's execution environment, serializes the program input parameters, calls the program's entry point, and reports any errors encountered. Okay, now how does that serialization work? SPF loader serializes the program input parameters into a byte array that is then passed to the program's entry point. There we go. So, what Solana does is when an instruction on our program is called, it basically creates us this byte array. That's the runtime that does that, I guess. And that will have all the information of the accounts and the instruction data. And that's what we get into a program. The entry point function gets this one byte array. This is passed onto the program's entry point. And then the program is responsible for deserializing it on chain. And that's exactly the part that I want to have a look at today. How does that deserialization work? And yes, there are frameworks or implementations that already do that. When you write your Solana program, you don't need to always write the code for that because there are functions that do that already. There are libraries, that's the right word, that do that already. So really you don't actually need to understand that. But when you understand it, and that's my goal for today, you just have more power. Because you can start optimizing things or, I don't know, find other ways how to play around with stuff. Or try and hack stuff, although not recommended. I mean, that's not what I'm trying to teach you here. But, you know, basically what I want to do is have a better understanding of how Solana works. That's it. I want to have a better understanding of how Solana works. That's why I'm doing this, and that's why I'm also teaching you this. Or really, I'm taking you along on the journey of trying to learn it myself. That's the way I teach, because I think it's the most entertaining one. Right. Wow, and there's even a difference between the loaders. One of the changes between the deprecated loader and the current loader is that the input parameters are serialized in a way that results in various parameters falling on aligned offsets within the aligned byte array. Oh, that's a sentence. What does that even mean? So for the current loader, parameters are serialized in a way that results in various parameters falling on aligned offset, I guess. So that serialization changed between the deprecated and the current loader. This allows the serialization implementations to directly reference the byte array and provide aligned pointers to the program. Oh, that's nice. Cool, and then we have Rust program parameter deserialization. There are helper functions that deserialize the program's input parameters into Rust types. The Entrypoint macros automatically call this deserialization helper. So that's automatically called with that Entrypoint macro. That's why in Rust, when you write a Solana program in Rust, you just define the entry point, done. That's all done for you. And we can have a look at that, what this deserialize actually does. What do we get? The input also as a U8, as a mutable U8 pointer. Same thing, just different language. And what we get is a pub key for the program, a vector of account infos, that's the accounts, and then an array of U8s as the input data. That's what we return. And here it works with offsets, not with moving the pointer along, because Rust, not C. Funny. Yeah, but we see it seems to do the same thing. Number of accounts, it just calls the variable differently, it does the same thing actually. It input add offset. Right, it steps further with the offset, which is 0, and it takes that pointer as a const U64, interprets that as usize, and boom, pointer, there we go, number of accounts. Similar thing, or well, actually same thing, just written differently because now we're reading Rust. And then we have the number of accounts. That's exactly the same as we see here, just that this is C, the deserialize in C, and this is the deserialize in Rust. So they seem to do the same thing. And then come accounts, and then somewhere comes instruction data. And at the very end, the program ID, which it also gets from the input. Okay, so even the program ID itself is in this input array. Do we see that here as well? So that's probably then the accounts, and that's probably then the input data. Yes, so the data length and then the actual data. It just sets to the current pointer because it always moves the pointer along, and then the data comes at this input. That's really smart actually, because it basically just works with those pointers directly. So it always references that area of the memory such that we never copy something that we would then need to move back, but we actually work on that data. And now my question is, when we're done with our program and we made changes to the state, like, I mean, this input data here is not really state, but like those things are like the Lamperts or the account data, that's Solana state. If that is changed, because we are working on that, does it write that back? Probably, because all we do in our program is change that value. So that's the pointer that actually points somewhere into this array here. And then we just change that and we never, write anything. So I'm assuming that that's automatically persisted. This function does not perform copy deserialization. Any modification to Lamperts or account data take place on the original buffer. Doing so also eliminates the need to serialize back into the buffer at the end. Yeah, so that makes me assume that that buffer is then also what the runtime again takes to, persist state. So yeah, I guess that's how that works. And probably in Rust as well. So that's the program source entry point. Pretty cool. Okay, so what do we do today? Step 1, understand how that works, like how the deserialization works, what data comes in which order. So basically reading this. And then I want to play around with this function myself a bit. And then I want to have a look at other implementation for entry points, like the one from KV or this one, Solana non-standard entry point. Because the entry point function in Solana is grossly inefficient. Unlike the usual entry point, it reads everything with no copies and no allocations. So probably the Rust implementation of the entry point is relatively inefficient. The C entry point, from what I've seen, doesn't seem to be that inefficient. At least I don't think it copies anything. I mean, it says it here that it doesn't copy. Yeah, let's start with that. Let's start with C. But also, no, really, we start with text. Some Solana programs may want to perform deserialization themselves, and they can by providing their own implementation of the raw entry point. So that's the actual thing. The raw entry point, programs export a known entry point symbol which the Solana runtime looks up and calls when invoking a program. So that's how that really works. That's what the runtime looks for. And yes, now we know it is the runtime. It is the runtime that looks for this specific thing, that takes a U8 pointer and returns a U64, which I guess is the return value then, the OK. Solana supports multiple versions of the loader, and the entry points may vary between them. Programs must be written for and deployed to the same loader. That makes sense. If it's written for a different loader, then this will not work because it won't manage to deserialize correctly. But I guess we don't need to really worry about that because nobody really uses the deprecated loader anymore. Hopefully, I guess. It's all just for this. So this is, I hope, what we're gonna have a look at today. Both have the same raw entry point definition. The following is the raw symbol that the runtime looks up and calls. The raw symbol is just C function entry point. Unsafe extern. Yes. The entry point takes a generic byte array which contains the serialized program parameters. So that's program ID, accounts, and instruction data. I don't know what etc. is. It's those three. Well, maybe the loader has some more information. I don't know. To deserialize the parameters, each loader contains its own wrapper macro that exports the raw entry point, deserializes the parameter, calls a user-defined instruction to process the function, and returns the result. Yeah, so that's what we usually use then, this user-defined instruction processing function that we usually call entry point or process or whatever, and do that entry point macro above. And that would look something like this, a function with a program ID, accounts, and instruction data. Cool. Now to the interesting part of the actual parameter deserialization. Take note that the provided deserialization function retain references back to the serialized byte array for variables that the program is allowed to modify, like Lamperts and account data. Yeah, so here again we see that that part of that input byte array, if that is changed, that changes Solana's state. The reason for this is that upon return, the loader will read those modifications so they can be committed. Yeah, that's what I'm saying. Now we got it confirmed in docs as well. This data is then being stored as Solana state. If a program implements their own deserialization function, they need to ensure that any modifications to the program... Yeah, so basically if we do some other deserialization, we need to ensure that the changes also go to that input byte array. Makes sense. Details on how the loader serializes the program inputs can be found at the input parameters deserialization docs. All the way down here. Okay, the latest loader, so that's the non-deprecated one, I guess, serializes the program input parameter as follows, all in little endian. So, number 1, 8 bytes unsigned number of accounts. That's what we saw here. 8 bytes for the number of accounts. Don't ask me why they call it KA. This still doesn't make sense for me, but you know. And then for each of those accounts, so that now depends on how many accounts we have, but for each of them, we will have 1 byte indicating if this is a duplicate account. If not a duplicate, then the value is 0xFF. So 255 if it's not a duplicate. Otherwise, the value is the index of the account that it's a duplicate of. Right. So why would you want to do... Okay, that makes sense. I get it. Right. Example, you do something weird, like sending from your own account to your own account, and you do a system program transfer instruction, right? Then you have twice the to account, you have the from account and you have the to account, but they're the same. So the runtime, the loader, will only serialize the entire account, you know, with all its data, and lamperts and data and flags and whatever. If it's a signer, all of that stuff, that's a lot of data. It won't write that twice, it will write it once, and then the program expects the accounts in a certain order though. So you need to provide the accounts. The first one is always the sender and the second one is always the recipient. That's what the system program transfer expects. And if they're the same, we have a duplicate. So therefore it then just tells me, oh, it is a duplicate by saying 01 for that, or 00, that's the first account that you've already read earlier. This is just a duplicate of that, which also ensures that there's just one reference to the lamperts and account data, because otherwise you might get inconsistencies. If it's the same account but you have it twice in memory, then you know you write the lamperts from the one but it's actually the same as the other one. That just, you know, it wouldn't work. So obviously we need to allow for those duplicates to ensure that programs still have the same order of of accounts, but each account is just serialized once. Cool, I get it why that is. So that's the first byte. And if we have a duplicate, then it's just 7 more bytes of padding such that we have, you know, multiples of 8. That makes sense. But if it's not a duplicate, then we have a bit more, a few more bytes. Let me guess, the total of that will also get to 8 before we get to the bigger ones. Yes, it does. So another byte if it's a signer, so that's the signer flag, another byte for the writable flag, and another byte for the executable flag. So encoded in bytes, the runtime will give us all of that information. Even though it comes from different origins, the isExecutable comes from the on-chain state. You know, each account has an executable flag. And the isSigner and isWritable, they come actually from the transaction. The highest privilege will be put here. Or actually, we had a look at this. You can remove privileges as well, though, if you call the if you do a CPI. But let's say we are on a top level instruction that is directly called from the transaction. Then this flag comes directly from the transaction if in the transaction this account is marked as a signer. And here, if this account in the transaction is marked as mutable, then this flag is set. Okay, and then 4 more bytes of padding such that we get to the 8 again. Okay, cool. What then? Then we have, that looks like a public key, the account public key. Yeah, public key, I said it, it's a public key. That looks like another public key, it's the account's owner public key. So first the address of the account itself, and then who owns that. That will usually be the system program, or, you know, the program owning that account. For instance, your program, if it's a program account of your program, or might be the token program if it's a token account, you know, the owner of the account. Not the authority, different things. Long time ago I made a video on, you know, that topic up there. Then 8 bytes unsigned number of Lamperts. So that's again from the state like this. Just that this we can't change. Even if we were the owner of the program, we can't just write that because only the loaders are allowed to do that, I think. But Lamperts, if it's writable, then we can just change that. And we can add to any account, and we can only remove if that account is also a signer, but that's stuff that the runtime checks. Here we just see that the next 8 bytes is just a Lampert field in that account, and then the next 8 is number of bytes of account data. So these two are the things that we can actually modify, the Lamperts and the account data. And because the account data can have different length, you know, depending on how much data there is on the account, we need to first also find out how much data is there. So we get that in our input array and need to deserialize that and then read that number many bytes for the account data, or deserialize that now as account data. And then we have 10 kilobytes, that's a lot, of padding used for realloc. I think that's also the reason why you can only realloc in increments of 10 kilobytes, at least for, you know, regular accounts like this. But I might be wrong, but that's just a guess. Yeah, it seems like a lot because we still didn't read the instruction data and there come 10 kilobytes. But yeah, we can just skip over them. 10 kilobytes of padding. Wow. And then enough padding to align the offset to 8 bytes. So in case the data has a weird number like 2 bytes, or I don't know, 259 bytes, that we, you know, get to a multiple of 8 again, because we like multiples of 8s, because then we can, you know, work with U in 64 sizes as well. Anyway, so if there is 1 byte, then we will add another 7 byte. If it's 259 or whatever I said, then it's gonna be 5 of those 8 bytes, just so we get back to the 8 byte padding. This is gonna be difficult to deserialize then though, or just, you know, some more code. And then we have 8 bytes a rent epoch. Don't even want to get into what that is, but that also comes from state, I think. And then we finally get to the instruction data. So that's now for all of the accounts. So if we have, you know, 5 accounts, then we do that 5 times. And then we get to the actual instruction data. But first, again, like here, we read the number of bytes that come as instruction data, and then comes the actual instruction data. And then in the very end, the 32 bytes for the program pub key. Okay, that's a lot. My throat already hurts from just talking through all of that. So now let's actually do a quick check if that is the same in the actual implementations, which I guess it will be. Here we read the number of accounts, and then for each account, we check if it's a duplicate. If it is a duplicate, if it's 255, no, that means if it's not a duplicate, then we read all of that thing. And here's the thing, when it is a duplicate, then we just have the padding and we push the thing that we already read. We basically clone it, push that into the accounts. And when it's not a duplicate, we read if it's a signer, we read if it's writable, we read if it's executable, we add the 4 bytes of padding, then we read the account pub key, we read the owner, again, always as pub keys, then the Lamperts. And this is interesting because that's a ref cell. I think we need to do that such that this part is actually mutable and, you know, can be changed, this part of this input. Like if we write there, that it actually writes into here. And the same with the account data that we have here. First, we read the length of the account data. And then we add to the offset the max permitted data increase, which is 10 kilobytes. Maximum number of bytes a program may add to an account during a single realloc. Back to our deserialize. And then is the weird thing with the offset, the padding. So here it checks the alignment to a U128. Wonder why to 128 and not to U64. Whatever. But I also don't know what those functions actually do. So whatever. And then it reads the rent epoch and then it pushes that as the account. So that's the accounts. And then the same thing for instruction data. You know, read the length of the instruction data and then the actual instruction data. And at the very end, the pub key. Cool. Does it match with our function in C? Yes, probably. We loop over all of the accounts, check if it's a duplicate. If it is, then we use padding and continue, lol. There comes the, if it was a duplicate, we copy all the things from the other account where it's the duplicate of. And if it was not a duplicate, it's basically just moving the pointer along what it does here. And that's the weird thing with the padding, to have the offset of 8 first minus 1, because we already have it does exactly what is described. It's a fun way of doing it and difficult to read, but yeah, fun. And then the actual reading of stuff. Wait, if I is bigger than number. Okay, so we specify ka number, so we specify how many accounts we want to read. That's what's happening here. That's why it's just moving along the pointer size here. When it's already above that number of accounts that we want to read, that we're interested in, then we don't need to deserialize them anymore. So we just skip it. All of that size for when there is an account present, and just another 7 to this one if it's a duplicate. Okay, that makes sense. But the actual way how it's deserialized when we're actually interested in it, that comes here. Okay, that makes sense. Okay, so there is signer, there is writable, executable, the key, and it's always basically just, typecasting the pointer directly, because C is fun. That's why C is so efficient as well. It's just like, yeah, take this, basically always just writing the pointer into here. It always just writes the pointer at the address. It writes the address into memory, into those fields. And, C doesn't care. We established that last time. And then again, this max permitted data increase, and then this padding. Fun. And then same for the input data. Yeah, nothing special here. Okay, that's cool though. And it is in fact so cool that I'm gonna play around with this some more in C, because why not? It was so much fun to work with C last time. So can I come back to my program, make sure that's deployed? Gonna delete this and make again. There we go. Because then we also get this output to deploy again. 4 transactions, such fun. We got the C program to transfer Lamperts deployed. And then we also had this nice transfer script. And because I'm lazy and don't always want to just copy transactions, I'm just going to simulate now. Boom. And then I don't need to actually send the transaction. I'm just going to estimate the CUs. So TS node, check that. Wow, this time it takes 400. What am I doing? Why did that take so much? Because I'm also creating an account. Right, I need to create that account such that my program can, have Lamperts. I could either not do that and reuse an account that I've already created, or try and figure out how to get that estimate for, I think easiest just to remove it. Because then we see how much the minimum transaction actually takes. I'm gonna actually execute it once. Like this. There you go, execute it. We have the transaction. Oh, that's funny. And now it tells me 150. That's weird though. So we've created this account and removed 3 Lamperts, or 300. I'm gonna copy this account, the 2DSS, do a new script where I don't do that. And the new account, we call it program account, is this address. There you have it. Then I just put in the program account here as writable. And now we don't need to create an account every time. Let's see if we run this. And now we actually also send the transaction just to make sure that's actually what's happening. And this in total uses 166 compute units. Because even though before we saw that the actual... Oh no, that also used 155. I thought that was just too big because the total was 315, but that's because there was another system program instruction. Okay, no, so actually this one transaction really just takes this much. So anyway, so we're at 166 compute units just for this part. And here it estimates 316. This estimation is weird. If I let you do it again 316. In reality, it's 166. Oh, I remember, because that weird get compute unit estimate for transaction always adds the instruction for the compute unit program, and that's another 150. This is so useless. I don't care. Let's just use the 316 as reference. Yeah, you know what? No, I'm gonna... There you go. No, this, you're not gonna fool me. There you go, 166. Accurate again. Fixed it. Easy. Right, so I'm simulating the transaction and just getting the compute units because we're always doing the same thing in the transaction, and I want to see if I can do the same thing more efficiently. That's my goal now, because that's essentially what we're trying to do here, learning and being more efficient. And my attempt now is to write my own deserialization function. Yes, exactly. Easy as that. I don't think I'm gonna be much more efficient than this because this is already very efficient, but I wanna try. And basically I'm just gonna refuse to deserialize it all the way into this sol account info. What do I really need? I wanna read the amount of Lambert because I still wanna have the same functionality. So I need to read the input data, and I will need to read the source and destination Lambert field. Everything else I don't really care about, including that check that you only provide me 2 accounts. You know, if you provide me 3, it will also say not enough account keys, just saying. But you know, that's a bug. If you call it with 3, then it should error actually, but not maybe with this error code. But it doesn't matter. Anyway, so maybe I don't want to do this. Or I do, and I just don't set all of the values correctly because I'm not going to read them anyway. Yeah, maybe let's do that. We still pretend that we have 2 of those, and then we do a my deserialize of the input and the parameters. And I don't care how many because I know exactly how many. It's my freaking function. Hold on, it's C, so I need to say what that is. The input is a const u int 8 pointer. Parameters are these, you know, like here. But I don't want to cheat and copy code from here. I'm gonna write it myself. Okay, then instead of the sol deserialize, we do my deserialize. We know exactly how much we take. So, man, I haven't coded in C in a while. But it can't be so difficult because as we saw accidentally last time already, the first thing that comes is the amount of accounts. That's something we could read, or we're like, we know it's 2, but I should probably read it. So let's do a U64 is input as, oh wait, hold on, this is Rust. U64 pointer cast input, make it a pointer, number of accounts. There you go. And then I could do it like that where I move the input along, but maybe it's easier for you to understand and potentially even more efficient, but I don't think so. I'll just have an offset and I'll just step it. I'll just do a, well, I would say U size, but that's not a thing that it has. Use this for now. What do I need to do? I need to go over all of the accounts, check if it's a duplicate, and see, I'm willing to make trade-offs now that probably I should not, like in a proper program, I should probably, you know, opt for reading the data and checking if it's correct. But I'm gonna make the assumption that there are exactly 2 accounts that I get and that they're different. On the other hand, no, you know what? We're gonna read the duplicate. We're gonna read it for each account. Gonna check. Wait, offset should be 8 in the beginning because 8 bytes for that number. I'm gonna check if duplicate, which I read once again from here, is already a U8, so I don't really need to typecast this because it is already this. I don't need to typecast, but I need to say input plus offset, which is the same as this, by the way. Fun fact. Probably easier to read, but teaching you some ugly C. Although I'm not sure if I need to not do this just to make sure. C is weird. And if this duplicate is not 255, oh yeah, we're in C, I need those, then I'll return false because I don't allow duplicates. Just my way of saying this. Because I don't want to deal with duplicates. And otherwise I now deserialize my account properly, except I don't, because I don't care about most of the things in the account. The runtime is gonna kill me anyway if I write to a non-writable account or whatever. And I don't need any of them to be signers, so whatever. So all I need to figure out is that Lampert's stuff. And that for all of that, and then the input data. So Lampert should still be quite straightforward. It's just some offset counting. So we had the offset until here so far, byte 1. So we have 8 until here, plus another 32 is 40, plus another 32 is 72. 72, and then comes the then comes the Lamperts. So let's do offset plus equals 72. And let's read directly into those parameters. Number I, Lamperts is this again. Again, just reading at that part of the input. And yes, I could save that offset and just add the input, and that would make it more efficient. I agree. But let's keep it that way and see how we compare in the end. Then comes the problem again, because this is not nice. But actually, I'm just going to do the same thing as with a duplicate. I'm not going to allow accounts that have data. So I'm going to read the data length. And if the data length is not 0, I will also not allow this, because then I can be sure that the data length is actually 0. So I can add the 8 bytes for the data length, the 0 bytes for the actual data. What comes next? The 10K of padding, and then enough padding to align to the next 8 bytes. And since I know that this has 0, I don't need to do that weird calculation with the alignment. So basically I just add 10 times 124 for 10 kilobytes. And the compiler will hopefully make this a static number and not do the actual calculations. But as we established, the C compiler is highly optimized, so I'm sure it will. Okay, and then another 8 bytes, so another 8 bytes, there you go. And then we're done for each account. End of loop. That was accounts. Now for the input data, which basically just read length as a U64, and then that's something that we need to access again, so I'll write it into the data. Oh, actually I could write the data length here as well directly. Data length, and then data, and I just write that same thing, just +8. Lol. Cool! Do you think that's gonna work? And I'm gonna ignore the rest, the program. I don't need to deserialize that. I don't need to know my own program ID. Do you think that's gonna work? I think it's not gonna work, but I'm gonna give it a try anyway and see if I can deserialize that. So basically all I did is I ignored a bunch of stuff, which makes my deserialize function a bit more efficient though. But you know, if I don't need that stuff, then I don't need to deserialize it either. So, and yeah, having some assumptions of what my accounts can be, then it can also be more efficient. And yes, it's not the most efficient implementation with that offset, but again, maybe even the C compiler can optimize that away, so it's fine. Probably it won't. Anyway, let's compile it. Make it. Oh, nope. I don't know how to write C code. Oh, call of undeclared function. Oh yeah, right, because in C, you need to define the function before you actually use it. So there you go. Let's write it a bit further up. That was number 1. What else? Incompatible integer pointer conversion. From uint to const. Okay, it doesn't like that as a direct... Oh, to non-const from const. That's the problem here. Okay, so Lampert's... Yep. I mean, basically you just need a typecast. That's all you need. Unsigned long pointer from unsigned long. Oh, you need a pointer. That makes sense. Ah, yeah, we read the actual thing by doing that. And here we just set the pointer. And here we read what's written there and get the actual data. Yeah. We deref this. And then what's the next error? Non-void function does not return a value at all paths. Yep, that's true. If everything works until here, I return true. That will hopefully do. Wonderful! Look at that. I could at least compile. Can I also deploy in a total of 4 transactions? Yes, I can. Will it also work? I don't think so. I'm gonna first just simulate. and get them minus 102 compute units. That seems realistic. What? Are you now not adding the 150 again or what? What's this about now? What the hell? If it's failing, it's not adding the 150, but that tells me it's failing. Okay. Can I have like the actual RPC simulate transaction API? But I don't know how to simulate with the new Web3.js. I should really figure that out because I did it already once. Okay, no, before I can't be bothered and look at it on chain then. Oh wait, actually that thing should already do the simulation for me. Hold on. Yeah, there you go. There I get the simulation. Insufficient account keys for instruction. That error comes from my program because I say not enough account keys. Oh yeah, because I'm not writing this. I'm reading it though. I mean, okay, sure. So I should write this. Okay, you're right. We're gonna write this in my deserialize because the number of accounts, I read it anyway. Let's just not read it into the number of accounts, or also set this then to the number of accounts. There you go. Make me that, deploy me that, and simulate me this. It simulates with 135 compute units. And not just that, it not just simulates, I actually sent it as well. Look at that, 135, and it did exactly the same thing. Minus 300 lamperts with just 135 compute units, which means my implementation of this deserialize is more efficient than the previous 166. Which also does the same thing. So what did we learn? I mean, what's the point of all of this? You can be more efficient by, decoding it more efficiently. And my way of decoding it more efficiently right now was just to, ignore some stuff that we might need, but we don't need in that program. So therefore I just don't read it, like, the data of the accounts. And that makes it more efficient. And really what I wanted to prove here is that I understand how the deserialization works. And since we get all the way to here, to the correct instruction data, it seems that this implementation is correct, because otherwise it wouldn't have read the 300 and, transferred actual 300 lamperts, or whatever I specify in my script, make it 303 now. And that will also work. Now sending 303 lamperts. It can deserialize the instruction data, which comes all the way after the account information. It first needs to read the info for those two accounts. It did make some assumptions, like that they don't have actual data on there, which I guess is fine, because the program knows what it expects. And it wouldn't send to an account that has data, for instance. If I give it an account that has 3 bytes of space, then my deserialization won't work anymore because the implementation is stupid. But also, this won't work. It tells me invalid program argument. Why? Well, because I return false here, and then this thing will return me the invalid program argument. My deserialization works. It just doesn't support data. And that's good. It's cool. It also doesn't support duplicate accounts, so I couldn't send from the program account to the program account. That will also end up in this invalid program argument. No duplicates, damn it. Yeah, cool. We understand what that input is and what it looks like, how we can deserialize that. If we want to do it in a more efficient way, we could now have a look at it in Rust. And you could do the same exercise here and, do that deserialize a bit more efficiently. And people have done that. The standard entry point is not necessarily the most efficient one. You can use a different entry point to save CU. For example, the no standard entry point from KV. It uses unsafe Rust though. You can read some comparison on different entry points here. There's Pinocchio, Solana non-standard, and the Solana program. So the non-standard is from KV and Pinocchio is from Fibo. And depending on how many accounts it deserializes, the Solana program one gets pretty inefficient, whereas those still stay pretty strong. And I don't want to go through the nitty-gritty of the implementations of those two. I just want to have a quick, first of all, I just want to tell you they exist and have a quick look maybe if you can spot anything that is different. Where's the Pinocchio implementation? Here. Declare the program entry point and set up global handlers. The main difference from the standard entry point macro is that this macro represents an entry point that does not perform allocations or copies when reading the input. We've seen this. So this is what we need to define. That's what the runtime looks for, this entry point, and it will give us this U8 array. And then it does the deserialize, calls this instruction. Returns either the success or the error. So what we get apparently is the error code that we return here. So this is probably the error code. And success, let me guess, is 0. Yes, 0. As you would expect in C. If you have a number for return value, it's the error code, then 0 usually represents there was no error. Nice. So this deserialize, we find it down here, total accounts as the first one. So do we now find a difference between this implementation and the implementation from the Solana program? First, it goes through all accounts, total accounts or max accounts. So we can have a max accounts, same as we saw in the C implementation. For how many we process, check if it's a duplicate. If it's a non-duplicate, we add the offset again and write account info raw account info. So first we just put the raw stuff at the offset of the input. Then we go the rest that we don't really process, we just skip them at the right size. Do the instruction data as well and the program ID. So here I don't see any real difference, just that it doesn't really deserialize it yet, but just works on just sets one pointer, and that is that raw account info. Then somewhere along the way you will deserialize that, I guess. So yeah, of course the entry point is faster if you don't do any deserialization there. I mean, that's also how we did it essentially. We don't write those unless we need them. But then that account info, that account info really just has the raw pointer to the account data. And then when we need stuff, then we have the implementation for it. Like if we need the key, then we decode that, or the Lampert's. Cool. So yeah, so Pinocchio does that pretty neatly. Here it has the account layout, and that's why it then knows. Basically by first casting the raw to an account, then we can say .key. Nice. Pretty cool. Now, the KV's Solana non-standard entry point. What's cool about this one? It is more efficient. But why? How does KV do it? Also uses this, then unsafe, deserialize, no standard. Account infos from raw parts. Then it also calls the process instruction. So first, deserialize. Can we spot the difference here? Yeah, again, basically we have the account info as input at offset as a mutable pointer, write a non-standard account info with the inner. So same thing, we just store that one pointer, skip the other accounts that we don't want to look at. Instruction data looks pretty similar, program ID. And KV has different implementations for the deserialization, either with duplicates or no duplicates, and either with program or no program. Then it just doesn't read the program if we don't need it. No standard account inner info, there it has the borrow state. So this seems very similar to what we saw before in the Pinocchio. So those two non-standard entry points seem very similar in that way. And I don't want to go into the very details on what is exactly different, mainly also because I don't know. But I'm happy enough in just saying those libraries are more compute efficient, maybe not safer, but more compute efficient than the standard entry point from Solana program. And you be the judge if lower CUs is what you need or if you don't care. Especially if you're using lookup tables and have a lot of accounts, then this adds up. And that's just for the entry point, not for anything of your program. And I don't know how efficient you need to be. In the grand scheme of things, I mean, what are 10K compute? But you know, it's a 10x. I think we're good here. The most important thing for me was to understand how this data comes in, what the program runtime actually gives to our program, and how it actually gets in there. And from here, you can do your own research and see what program entry point you actually want to use, if it makes sense for your program to use a non-standard one, if you want to build your own one, all fair strategies. Or if you're fine with just taking what the Solana program library gives you. Good! We learned some stuff. This is not nice code, but it works and it's more efficient. And that's all that counts for me. Job done. But your job just started. Or did it? I don't know. But yeah, thank you for watching. And if you want to keep watching, there's more stuff that you can check out. I'm making a lot of videos that you can like. You can subscribe to this channel. And yeah, support me by telling me if those videos are useful or not. Or what else it is that you want to see and have me investigate. For now, I mean, mainly I'm just following my curiosity and, you know, checking what I want to look at. And maybe you have something that could also spark curiosity in me. It would be cool. Leave me a comment. And then I'll see you in that next video where we have a look at the next thing. Now that we know how that entry point works, maybe next step would be to decrease our usage of compute units even further by coding in assembly. Because really, we don't need any of that. We can just directly modify one value in the Lamberts and be okay. And, you know, I can also do that with C, but at least I then want to understand how it works. Knowing how the input works, I think will help us also code in assembly. So yeah, I wanted to have a look at that first. And we did now. Good job. See you in the next one.